Welcome to the TEEP Podcast, brought to you by the State Energy Conservation Office in Austin, Texas, and Energy here in Houston, Texas. I'm your host, Gary Gildert. I'm joined by Communications Director Benita Roy and PhD student Shahriar Hussain. Communications Manager Brenda Cruz and intern Christian Garcia are in the background making things happen. We bring you the latest in industrial energy efficiency in 15 minutes or so. First off today, we have upcoming events with Benita. Tell me what's happening out there.
Thanks, Gary. So first up, we have the Chevron Innovation Competition. The Elimination round is on July 24th, Friday, from 2 p.m. to 5 p.m. at the University of Houston. So this is the 5th annual Chevron Innovation Commercialization Competition. It's a dynamic event that empowers students to transform cutting-edge energy research into real-world solutions. This event is sponsored by Chevron and coordinated by Energy, underscoring our commitment to innovation, entrepreneurship, and energy transition leadership. The registration link is available on the Energy events calendar. Next up, we have the 2026 STEAM System Masterclass workshop. This is going to be held on August 20th and 21st at the University of Houston Technology Bridge. After hosting successful masterclasses the last 2 years, TEEP is organizing the STEAM System Masterclass workshop in 2026 also. The workshop is taught by James R. Risco, MBA, CEM, PEM, presenter, consultant, author, and inventor. Jim is a retired president of TLV Corporation in Charlotte, NC, formerly responsible for US and Canadian operations. The registration link will soon be available on the Energy events calendar. We'd like to remind our audience about SPEAR. You can check out their websites for webinars and information for small and medium industries as well as commercial properties. All our TEEP podcasts are available on YouTube. You can check out the Energy YouTube page to access them. We are also now on Spotify. This month, we'd like to highlight APTIM Federal Services LLC, which through its partnership with the Texas State Energy Conservation Office is hosting free in-person community events this summer to share and gather input on the new Texas Home Efficiency Rebates, or HOMES, and Home Electrification and Appliance Rebate, or HERE, programs. These programs will provide rebates to eligible households up to $8,000 for homes and up to $14,000 for HERE, to make energy efficiency improvements and reduce energy costs. The events will cover an explanation of the HOMES and HERE programs, program benefits, anticipated launch timeline and process, an opportunity to provide input, and where to find updates and next steps. Check out our newsletter for the registration link. Also coming up, in October 22nd and October 23rd, is the Southwest Process Technology Conference. Gary, please tell us more about it.
Thanks, Benita. I'm looking forward to this event because SPTC features 2 energy efficiency sessions. Now, the deadline for the abstracts was June the 19th, but if anyone listening to this podcast has a good idea for an energy efficiency presentation, please submit it through the portal and send me an email so I know that it's there. Now, registration is open with early registration discounts and discounts for groups of 5 or more, so bring along a friend. Attention industry folks, we encourage you to become an SPTC sponsor to gain visibility for your organization and build relationships with prospective clients. Sponsoring organizations will have access to reduced registration rates for their members. So see the June newsletter for more details of this spectacular event. Last month, there were 2 events related to industrial energy efficiency. The Industrial Energy Technology Conference was on May the 19th to 21st at the Houston Marriott South. It featured energy efficiency and plant optimization technical topic areas. Now, 5 of those sessions were on energy efficiency, featuring a total of 10 presentations. Now, the focus was on energy management and system efficiency. what was interesting was there were a lot of mechanical engineers and electrical engineers and energy managers and not so many chemical engineers. But this conference really reinforces the benefit of learning about energy efficiency from people with different skill sets and points of view. I quite enjoyed it myself and got a lot out of it. Now, the Energy in Action seminar was on May the 29th at the Sugar Land campus, and the topic was digital twins. John Nixon and Ravi Aglev from Siemens were our speakers. I'll tell you, this was the best AI talk of the season. And yes, they reinforced AI will let us do more. But the interesting thing is, they emphasize that don't expect it to save a lot of time and money on engineering. What's the likely outcome is we will get better projects by examining more options and more cases. This means that this will include more energy efficiency options, and this can only be a good thing, especially for our area of industrial energy efficiency. What AI will also do by integrating all these systems is bring better communications between the disciplines. The likely outcome of that is improved cost and schedule on the construction. So perhaps that's really where the money will be saved. And our jobs, I think, are going to be quite secure with AI present. We'll just get to do more. The article in this month's newsletter was on propane dehydrogenation from Shahriar. So, Shahriar, tell me, what's so important about propane dehydrogenation?
Sure. So the answer is propylene. It is one of the most important building blocks in the petrochemical industry. Its largest use is in making polypropylene, but it is also used to make propylene oxide, acrylonitrile, cumin, alcohols, and other chemicals.
But why propane dehydrogenation? I thought we got enough from steam cracking and FCC off-gas recovery.
Yes, that is true. Historically, a lot of propylene came as a co-product from the steam cracking and refinery FCC units, but as feedstocks for those processes shifted lighter to ethane-rich feedstocks, those shale gas liquid steam crackers started producing less propylene relative to ethylene. At the same time, demand for propylene continued to grow.
Okay, I saw a lot of that too while I was in the industry. So let's see if you can tell us the basics in the chemistry and the thermodynamics of propane dehydro.
Yes. So the main PDH reaction, I'll call it PDH, propane dehydrogenation.
Go ahead. Yeah.
It involves the equilibrium reaction between propane, or propylene, and hydrogen. It is an endothermic process. It takes about almost 124 kilojoules per mole of propane that's reacted. And it's strongly endothermic, and heat has to be supplied. Since the reaction produces more gas molecules than it consumes, high temperature and low pressure favor propane conversion, according to the Lush-Clear's convention.
Okay. And what other reactions are going to take place? Because I know it's not 100% selective.
So these reaction conditions also favor cracking and coking reactions, which may end up making the process less efficient, but some processes can take advantage of the coke that is produced and burned off during regeneration. When you have cracking reactions, you also have olefins that are produced, which can be separated and then used either in situ with the plant or sold out as byproducts.
So which process parameters did you look at when you were comparing the different processes?
Our analysis considered 5 main process parameters. The first is the reactor temperature, because higher temperature involves equilibrium conversion, but also increases side reactions and heat demand. The second is reactor pressure, because low pressure improves conversion because it's in equilibrium, but increases compression load. The third is propane conversion, defined as the fraction of propane fed to the reactor that reacts. This matters because unconverted propane must be separated and recycled. The fourth is propylene selectivity, meaning the fraction of converted propane that becomes our desired product, propylene. Higher selectivity means less carbon loss and less burden on separation and regeneration. The fifth is the diluent to propane feed ratio. This differs strongly by technology. The more diluent you have, the higher the separation duty and the compression load.
Perfect. So which metrics did you consider in evaluating these different processes for energy efficiency?
We consider 6 metrics for this analysis. We consider the net feed preheating duty, the heat of reaction, compressor duty, regeneration, separation energy, and byproduct credit.
So which processes did you evaluate for energy efficiency?
Yes. So industrially, you'll have processes that use different reactor configurations. We used the 4 major ones that are industrially relevant. The first is cyclic parallel fixed bed reactor configuration. In this process, each reactor alternates between dehydrogenation, purge, and regeneration. Several reactors are staggered, so the overall plant operates continuously. The process operates at low pressures and relatively high temperature, giving good conversion. The downside is high compression demand and frequent regeneration.
Okay. And what was the second one that you looked at?
We then looked at the moving bed adiabatic reactor. Here, the catalyst moves continuously through a train of radial flow reactors and then to a continuous catalyst regeneration unit, which is pretty interesting. Interstage heaters restore the temperature between these reactors, and it operates at moderate pressures but uses hydrogen as diluent. Its strength is continuous regeneration and low coking severity, but the hydrogen diluent increases the amount of gas moving through the system.
And the third one?
The third is the fired tube reactor. It uses catalyst-filled tubes inside a fired furnace with steam mixed in the feed as diluent. The process operates at higher pressures than others, which reduces compression duty. It also includes an oxygen reactor where oxygen selectively combusts hydrogen. That provides heat and shifts the equilibrium forward, which is beneficial to the entire system.
And the fourth one?
For the last one, we looked at the fluidized or circulating catalyst reactor. In this mode, hot catalyst circulates between the reactor and regenerator. This can provide good heat transfer and continuous catalyst regeneration. Fluidized systems typically have moderate pressures and no major diluent, but it has high propylene selectivity, but they also require continuous catalyst circulation and coke management.
So what is your conclusion from all this?
It wasn't trivial to pick a strong contender out of it. We made a lot of general assumptions about the processes because the stream data is not widely available.
You mean you couldn't do a detailed techno-economic analysis of all 4 processes in the last week?
No, I wish I could, but no. Even in terms of the available data, that's the first bottleneck here. You can't make a detailed simulation, a process simulation of these processes without having some relevant data for all of the processes. And the way they differ is how they use heat integration, how they essentially even though the chemistry is kind of common in between these technologies, you'll have different strategies in heat recovery and separation. So you have to make some general assumptions to compare them, like apple to apple basis.
So in other words, there's no obvious choice, but on balance, I think you decided there's one that's a little bit better than the others as far as energy efficiency is concerned.
Yes, that is true. So that was our purpose. We wanted to look at the technologies in a way where we can shed light on which of these processes is using energy more efficiently. So our analysis showed us that the continuous moving bed process appears to be the most energy efficient overall. The main reason is that it combines low regeneration severity with a high byproduct credit. In other words, the moving bed operation avoids the frequent bed regeneration of, let's say, for example, the fixed bed reactors. It does not consume as much hydrogen as in, for example, the fired tube reactors. It also produces valuable hydrogen that can be recovered for use or sold.
So in other words, it's not producing a lot of coke, so it doesn't have to, and it's not using that coke, and it's producing some gaseous byproducts, which we have given credit for.
Yes.
And that really does make a big difference on the energy efficiency. Compression, some were better, some were worse. So tell me about the regeneration systems.
So for the regeneration, you'll see the continuous moving bed configuration has an advantage here. It's because of the much lower coking rate, and that results in it having much lower regeneration duty.
So what did you find out about the separation energy requirements?
Well, for the separation energy, we assume because the conversion and selectivity are pretty similar for these technologies, the product slate is also similar, and the separation techniques can be assumed that they don't vary too much in terms of energy duty.
So in other words, I didn't make you spend 2 weeks on each process to figure out a detailed simulation?
No, you did not. Thank you.
You're welcome. Okay, they all had different byproducts as well, so tell me about that.
Yes, the byproduct credit is also very important. You'll see that the continuous moving bed has an advantage here as well. It's because it has all the hydrogen available, and it's not burning anything during reaction.
Okay, so in conclusion, which one appears to be the most energy efficient process?
Yes, so from my perspective, based on this analysis, I see that the continuous moving bed has an advantage here. It's because of the lower regeneration duty and the high byproduct credit.
So based on your analysis, which process do you believe is the most energy efficient?
Yes, so based on the analysis that we did, the continuous moving bed process appears to be the most energy efficient overall. The main reason is that it combines low regeneration load with high byproduct credit. But the final decision for the selection process depends on site-specific factors, such as local feedstock availability and cost of energy.
Those are the important economic factors. Thank you for writing such an interesting article. I think there's going to be a follow-up on this as well as we look into some of your research on oxidative dehydrogenation. But that's next month. Thank you for listening to the TEEP podcast, brought to you by SECO and Energy. We were joined this week by Communications Director Benita Roy and PhD candidate Shahriar Hussain. And many thanks to Communications Manager Brenda Cruz and Media Engineer Christian Garcia. I'm your host, Gary Gildert. We bring you the latest in industrial energy efficiency in 15 minutes or so. We'll be back in a week or two with another interview.